On April 28, 1988, Aloha Airlines Flight 243 was cruising at 24,000 feet between Hilo and Honolulu. 95 people on board. A routine island hop, 20 minutes in the air. Then an 18-foot section of the fuselage roof tore away. Passengers looked up and saw open sky. Flight 243 departed Hilo at 1:25 p.m. local time. The aircraft was a Boeing 737-200, registration N73711, named Queen Lili Uoka Lahni. It had been built in 1969. Captain Robert Shaunst High-Mare, 44, was in command. First Officer Madeline Tompkins, 36, was flying the leg. At 24,000 feet and 1:46 p.m., a section of the upper fuselage skin separated from the airframe just aft of the cockpit door. The cabin decompressed instantly. Debris blasted backward. Passengers were struck by flying metal and insulation. In the cockpit, the noise was so loud that Shaunst, High-Mare and Tompkins could not hear each other or communicate with air traffic control by voice. Flight attendant Clarabelle Lansing, 58, was standing near row 5. She was swept out through the opening. Her body was never recovered. 65 of the remaining 94 people on board were injured, 8 of them seriously. The airplane was still flying. Shaunst, High-Mare and Tompkins could see daylight through the cockpit door behind them. They had no way to know how much of the airplane was left. Shaunst, High-Mare began an emergency descent toward Kahului Airport on Maui, the nearest runway. The situation in the cabin was extreme. Passengers were exposed to the open airstream at altitude. Floor panels had buckled. 2 of the cabin's emergency exits had blown open. The remaining flight attendants, despite their own injuries, moved through the wreckage, checking on passengers and securing them as best they could. One engine had failed during the decompression, ingesting debris. Tompkins flew the approach on the remaining engine. 13 minutes after the fuselage tore open, the aircraft touched down at Kahului. Everyone on board except Clarabelle Lansing survived. The photographs taken after landing are among the most striking in aviation history. The airplane sits on the runway with the forward third of its cabin roof entirely gone. Wiring and structural frames are exposed. The cross-section of the fuselage is visible, like a cutaway diagram made real. It is hard to believe this aircraft flew at all, let alone landed safely. To understand why the roof came off, you need to understand 2 things about this particular airplane: where it flew and how it was built. N73711 spent its entire 19-year career on Hawaiian inter-island routes. These are among the shortest scheduled airline flights in the world. A typical hop lasted about 24 minutes. Each flight meant 1 complete pressurization cycle. The cabin inflates on climb, deflates on descent. A long-haul aircraft might accumulate 2 or 3 cycles per day. N73711 was doing far more. By April 1988, the airplane had logged 89,680 pressurization cycles and 35,496 flight hours. That cycle number is the center of the story. During certification, Boeing tested a representative 737 fuselage half-section to 150,000 pressurization cycles. That was twice the economic design life goal of 75,000 cycles and 51,000 flight hours. N73711 had exceeded that design life goal by nearly 20%. But cycle count alone does not explain the failure. Other high-cycle 737s did not lose their roofs. The specific vulnerability was in the construction of the fuselage skin joints. The fuselage of any pressurized aircraft is a tube. Every time the cabin pressurizes, the tube expands slightly. The stress runs around the circumference, called hoop stress, and it concentrates at the joints where skin panels overlap. These overlapping seams are called lap joints. On early production Boeing 737s, line numbers 1 through 291, the lap joints used a bonding method called cold bonding. The overlapping skin edges were joined with an epoxy adhesive reinforced by a woven scrim cloth, then secured with rows of countersunk rivets. The adhesive was meant to distribute the load evenly across the joint. The rivets were back up. The problem was that the scrim cloth wickeded moisture. In Hawaii's warm, humid, salt-laden coastal air, water seeped into the bond line over years of service. The adhesive slowly disbonded. Once the adhesive failed, the rivets carried the entire load. Every rivet hole became a stress concentration point. And at each of those points, a tiny fatigue crack began to grow. This was not a single crack. It was dozens of cracks at adjacent rivet holes, all growing simultaneously. Engineers call this multi-site damage, or MSD. It is a specific and dangerous failure mode because it defeats the standard safety assumption built into aircraft structures. That safety assumption is called fail-safe design. The idea is straightforward. If a single crack develops in a structural panel, the surrounding intact structure stops it before it can grow to a dangerous length. Crack arrest straps, tear straps, doublers. The structure is designed so that one crack cannot propagate into a catastrophe. After the Havilland Comet disasters in 1954, every commercial aircraft was built this way. But fail-safe design assumes a single dominant crack. MSD breaks that assumption. When cracks are growing at every rivet hole in a row, the intact ligaments between them are too short to arrest anything. The cracks link up. Instead of one small crack being stopped by the surrounding structure, dozens of cracks merge into one long fracture in a fraction of a second. The structure goes from intact to catastrophic with no intermediate warning. That is what happened on N73711. At lap joint S10L, the cracks linked. The fracture ran along the rivet line, the fuselage skin peeled away. The NTSB investigation assigned probable cause to Aloha Airlines maintenance program, which failed to detect the disbonding and fatigue damage at the lap joint. Contributing factors included the FAA's failure to mandate lap joint inspections that Boeing's own engineers had proposed, and the absence of any required fix for the known cold bond durability problems on early 737s. The consequences were broad. An Emergency Airworthiness Directive, Airworthiness Directive 88-12-04, required immediate inspections of cold bond lap joints on all early production 737s. The FAA launched its Aging Aircraft Program, funding research into MSD, corrosion, and high-cycle inspection methods across the entire commercial fleet. In 1991, Congress passed the Aging Aircraft Safety Act, requiring structural inspection programs for aircraft beyond defined age and cycle thresholds. The Comet crashes taught the industry that metal remembers every pressurization cycle. Aloha 243 taught a harder lesson, that the safety net built after the Comet had a hole in it. Fail-safe design works until it doesn't. At 89,680 cycles in a salt air environment with a bonding method that invited corrosion, the net failed. The fix was not a better net. It was learning to count the cycles and act before the cracks connect.